In this presentation, I'll be critically appraising the use of fall detection systems in a health setting. This technology mainly targets the older population as the World Health Organization identifies age as a key risk factor for falls. A wearable fall detector system can commonly be placed on a user's chest, wrist, waist, thigh, ankle or plantar aspect of the foot. This, however, opens the question of if the device has been tested for and is valid in all locations it can be placed. Wearable fall detection systems typically capture data using IMUs, which are inertial measurement units. This integrates an accelerometer, gyroscope, and in some models a magnetometer into one single component that can be installed into a fall detection device. Pressure insoles using an inertial system can also be used as a fall detection device. Some devices use a smartphone or smartwatch as a sensor rather than an IMU. However, practically all current smartphones and smartwatches are embedded with an IMU, so they can be used in fall detection systems. Shahar and Agmon in 2021 concluded that a single smartphone is valid and reliable for measuring human gait, as they compared it to the gold standard gait analysis system. However, this was only tested and consequently only valid when placed in a front-faced pocket. Devices include a GPS tracker to allow emergency services to be dispatched following a positively detected fall. This could, however, be seen as intrusive to the user and disrupt their privacy, but it can be viewed as a better alternative to a video camera setup analysing a consumer's movements. Various biomechanical data can be generated by the IMU in a fall detector system. This includes linear acceleration, which is measured by the accelerometer as it calculates the applied force using a spring mass system. Angular velocity is measured by the gyroscope, as when it is rotated, a mass inside the gyroscope gets displaced, causing a change in voltage. This change is proportional to the force experienced due to the rotation. The magnetometer is used to measure magnetic fields around the device. If the device is static, then the accelerometer can be used to establish orientation because only gravity is acting. During dynamic conditions, data from the gyroscope and magnetometers are necessary to establish orientation. There are various ways to detect if a fall has happened. Each device manufacturer has different methods at detecting a fall. This can be due to the type and number of sensors a device uses. The majority of fall detection systems use the accelerometer to detect high levels of linear acceleration. Orientation changes are also analysed at the same time. This can help the device figure out if a fall has occurred or not. Each wearable device technology designed installs a different algorithm using different datasets to work out whether a fall has occurred. Most wearable technology companies will generally privatize their datasets or algorithms to prevent other competition from replicating their technology and ideas. This also makes it difficult for researchers to critically appraise its use in health settings. However, there are studies that have reviewed the validity and reliability of these different algorithms. Igual et al. In 2015 found that performance of the detection algorithms may strongly depend on the employed samples. This shows that the difficulties a specific fall detection system may have if only checked against a single dataset. An analysis by Casilari et al. In 2017 obtained 12 publicly available datasets on wearable fall detection systems. Since the samples may be strongly relied upon by the fall detection systems to classify whether a fall has taken place or not, the demographic tested in these datasets are therefore important to determine if a fall detector is valid for the produced dataset populated from their demographic. From these 12 datasets, there is a male dominance of subjects used. This is significant in these fall detection systems' search for validity within a female population, as men and women experience falls due to different reasons. Men are more likely to fall due to loss of support from external objects, from a seated position, and while rising. Women are more prone to falling from tripping and walking. Generally, women are more susceptible to falling, but men have a higher fatality rate from falling than women do. The volunteers for these datasets are established by young adults with a mean age in testing of mostly below 30 years old, with very few over the age of 50. This is to be expected as the risk of emulating a fall in an older population can be deemed immoral. This also meant that the activities of daily living tested were limited to those that did not pose any risk in the interest of safety. Participants involved were indicated to be healthy and free of any disability that could affect their movement. This opens the discussion where the biomechanical data gathered from healthy young adults or athletes that are skilled to cushion impacts from falls can be extrapolated to the mobility patterns in an older population. This questions the device's reliability at detecting falls. Authors Majumdar et al. In 2014 found that the effectiveness of mobility pattern classifiers clearly plummets when the recognition of the dynamics of a certain individual is founded on another subject's gait. Contrary to these findings, Kangas et al. In 2012 undertook research that compared real-life accidental falls in older people with experimental falls in middle-aged test subjects. They examined the acceleration signals produced in the intentional falls and those captured in actual falls and concluded that they display similar profiles. This heavily supports that using younger participants' acceleration data to predict a fall has occurred is valid, as wearable fall detector systems use accelerometers to gather biomechanical data. The arguing study suggests that since a lot of testing for fall detection uses young adults as participants for data collection, that this could mean that the fall detection might be more valid for the tested population of below 30 years old. Quality of data in these devices is currently poor, as most data collected is where falls are simulated in a controlled environment and may not reflect real-life conditions. Furthermore, real datasets concerned with the fall patterns of older adults are not yet available. Consequently, it is important to create a user-friendly design to guarantee a higher quality of data for future research. Ecological validity is good in terms of the actions being undertaken, because testing activities are those of daily living like in real life. This is relevant since 60% of falls occur in the home. However, most of these studies are still performed in lab environments, which argues its level of ecological validity. Dataset produced by Cogent Lab and Sysfall were the only sample analysed that tested a special group of activities of daily living that were classified as near falls. This, however, made the fall detector produce a false positive during some of these near fall actions. With insole fall detection systems, most studies reviewed by Santoyo-Ramón et al. In 2022 obtained pressure readings at a sampling rate of 50 Hz. This is sufficient for walking. However, a higher sampling rate is required for those activities such as running, cycling, and stair ascent and descent. This may show how the fall detection system is only reliable in walking pace activities and unreliable in those activities requiring a higher sampling rate. Activities of daily living for those in the older population are generally quite slow movements, but the inclusion of stair use could cause reliability concerns with the insole use for fall detection. Several smart insoles currently available aren't customizable to the user's shoe size and therefore only validated for use for those individuals with the same shoe size as the product. Fall detection technology has been found that it is less accurate when worn on the wrist in comparison to devices placed closer to the user's center of gravity. Furthermore, devices worn near the shoulder give the sensor maximum distance to the floor, improving its accuracy of detecting a fall. As previously discussed, certain movements such as near falls and other common movements that produce high acceleration numbers may lead to false positives by the fall detector. Some may say it's better to have the owner to confirm through the fall detector that a false positive has occurred, because it is better than the device not registering a fall at all. This contributes to its value to society because, as Gjoreski et al. In 2017 discovered, that morbidity and mortality provoked by falls are closely connected to the rapidness of the medical response and first aid treatment after the incident. Therefore, having a false positive can be deemed better than a false negative, as the point of the fall detector is to reduce the time between a fall occurring to the medical response and first aid treatment. On the flip side, if a user experiences too many false positives, it may drive the individual to not wear their fall detector, which can put them at higher risk if a fall does occur. In a review of wearable sensor systems for fall risk assessment by Santoyo-Ramón et al. In 2022, they discovered that due to a long continuous data collection and follow-up period, most studies reviewed had insufficient sample sizes of mostly less than 100 participants. This does not allow for an efficient classification or prediction model for the falls to be achieved. A small sample size may result in the final classification model to be overfitted. Distorted models may also be produced with insufficient positive samples. It is unclear if results can be generalized, and therefore more testing needs to be done with a larger sample size, including diversity with regards to age, sex, and fall history. This can be used to validify the use of these fall detection devices in a wider range of individuals. A lack of standardization within different wearable devices make it difficult to make clinical determinations and comparisons between data acquired from these fall detection systems. Future research should be directed to distinguishing a standard protocol and data management to have consistency in studies around falling. A review by Igual et al. In 2013 deliberated that the number of studies using context-aware techniques are still increasing. This research can be used to help appraise fraud detection systems in a health setting. In their research, they also identified a trend towards the integration of fraud detection into smartphones and smartwatches. This means that a smartphone-only fraud detector system could be invalid sometimes, as it would rely on the phone to be placed in the front pocket all the time to be reliable to identify a fraud. The rapid development of such technology opens the question of if it's valid and reliable before implementing it into the real-world situations and relied upon by consumers. The accessibility to a wider population, however, increases the value to society of fraud detection systems because individuals and their families gain access to cheap and mobile equipment compared to previous systems. Since more people are using this technology, these devices should become better and more accurate at detecting frauds, as machine learning will increase as there is more real-world data available. This can therefore help contribute to the elimination of the invalid use of these devices because real-world data can guide machine learning away from only using its initial data sets it has been provided into its fraud detection algorithms. In conclusion, more real-world data is required to guide machine learning into creating a more valid and reliable predictions as to whether a fraud has occurred. Data needs to be collected from the product's target population to increase its validity within that demographic. Research needs to be performed with a standardized approach to allow for easier comparisons between studies.